Okay, so in this video, I'm going to talk about ways you can try to find the range of a function. Remember, the range corresponds to all of your y values that your function takes on. Whereas we spent a lot of time on the domain, which is finding the x values that your function takes on. To find the range of a function is not always as easy as doing the domain. We have more tools for finding the domain of a function than for finding the range. But you do have, I think of three options when somebody asks me to find the range of a function. The first thing you should think about is, could you just either graph it on paper or even just picture the graph of what it looks like? Then you could kind of identify what your maximum and minimum y values are just by thinking about the graph. So we're going to do some examples with all three of these techniques. As we saw on a previous video, where we found the inverse of a function, you could also take your equation and try to solve it for x so that you get y on one side of the equation, and you can kind of see what, if any, restrictions your equation would have on y. So that's part of the process of finding the domain of the inverse function, is something we talked about on a previous video. And then the third technique, which a lot of times this is, students get worried about this, is literally, sometimes you can find the range by just thinking about it. In other words, by inspection, by just looking at it and asking yourself some logical questions. So this is a technique. There's not really any set steps to this, but we'll talk. I have a couple examples for this one, how you can find the range of a function by inspecting it. So first of all, for these two examples, f of x equals 2 times x plus 3 squared minus 4, and my second equation, hopefully you recognize that those are two things we could fairly easily graph. You recall this is your base graph is a parabola, and the transformations here, the plus 3 is moving my vertex left 3, minus 4 is moving my whole graph down 4, and the 2 outside of my, not with the x, is going to have the effect of causing a vertical stretch. It's going to stretch my y values out, double my y values. So let's think about what this graph would look like. The vertex is going to be -3, -4. I know it's going to open upwards, and it's going to be steeper than a normal parabola. One thing I might do, I don't necessarily need the x-intercepts, but I might want to find the y-intercept. So I have a point that it goes through. If x is 0, this is going to be 3 squared is 9, plus times 2 is 18 minus 4, it's 14. So let's just call this point 0, 14. For these purposes, we don't need a super accurate graph. The main thing we need to see is that this vertex, which is -3, -4, corresponds to my lowest y value. So I can look at this graph and I can say the range of this function, the smallest value of y is -4, which includes, and it takes on every single y value up to infinity. Another way to think about the range too, analogy I like to use is, if you, once you picture the graph, if you can imagine smashing it into the y-axis, if you took both hands and smashed it into the y-axis, where would you see stuff? You would see stuff from -4 all the way up to infinity. So that's your range. Okay, the second equation, our base graph was the square root function, which, remember, starts at the origin and usually bends off to the right. This negative outside the function, not with the x, is going to reflect my y values, which means it's going to reflect about the x-axis. And then this plus 5 is going to move my graph up 5. So again, normally my square root function would start like this and move curve up. But since it's reflecting around the negative, around the x-axis, it's going to go down like this. And I'm going to move the whole graph up 5. So this point is 0, 5. And I know it's going to be a square root function that dips down like that. So in terms of the range, we always go from smallest to greatest. So how low will this thing go? It keeps going down forever. So my lowest y value will be negative infinity, and then my highest y value is right when it started, which was at 5, including the 5. So those two examples, I think the easiest way to do it is to just graph the functions and look at the range. For this next one, this might be a little bit tougher to graph, at least at this point in pre-calculus. We haven't really talked about graphs like this. It would not be based off a base graph that we've discussed in here. So I'm probably not going to graph it. So I'm going to use the technique where we're going to just try to solve this for x, because it doesn't look too hard to solve for x. We've done this before. So this is y. If I want to solve this for x, I'm going to move the 5 over. So y minus 5 is equal to 4 over x cubed. You can either multiply the x cubed over, or you've seen me do this before probably. I'm going to flip the right side, which means I'm going to flip the left side. So I'm going to have 1 over y minus 5 is equal to x cubed over 4, because I wanted x in the numerator. And then lastly, I'm going to multiply both sides by 4 to get rid of this 4. I guess it's not the last thing, but that means x cubed would be 4 over y minus 5, which means if I take the cube root of both sides, x is equal to the cube root of 4 divided by y minus 5. Now, yeah, if you were finding the inverse of this function, the next step would be to switch your x and y and call that the inverse. But if we just stop right here and think about what can y be and not be, remember that it's okay to take the cube root of a negative number or a positive number. So I'm not worried about the inside being negative. If it was a square root, I would worry about that. So the only thing I really have to worry about here is, of course, you cannot have y being 5, right? You're going to be dividing by 0. So my range would be all y values not including the 5. So we could write it like that in interval notation. Okay. Let's do one more like that. Again, that's not a graph that we have discussed. Very soon we will be sketching graphs like this, but at this point in pre-calculus, we have not graphed anything like that. So we're going to try to solve for x again. And this would be a good time to pause the video and see if you can get solve for x in terms of y and figure out the range. And then replay the video, assuming you've done that now. So we're going to move the x minus 7 over. So we have y times x minus 7 equals to, when I say move, we're multiplying both sides by x minus 7. We're going to distribute. Because my goal is to solve for x, I'm doing that technique again. I want to get these two terms on the same side. Easiest way to do that, I see, is to just trade positions. Add the 7y over here, subtract the 3x to the left side. Because then I can factor out the x. And then last step would be to divide. And at this point here, I can see that I have a fraction. There's no square roots to worry about. So like the previous one, the only thing I'd have to worry about is dividing by 0. This tells me y cannot be equal to 3. So in interval notation, negative infinity to 3, union 3 to infinity would be my range. Okay. And then my last two examples, we're going to explore the third technique that I mentioned at the start of the video, which is this. See, I don't think I could graph that. It is a square root, but this is not a base graph that's been shifted because of these powers, x to the 4th plus 2x squared. That's not, you can't think of it in terms of transformations. Hopefully you'll agree, if I tried to solve this for x, that would be very difficult because I'd have two x's here, right? To try to undo, that would be really tough. But on this would be a situation where to find the range, what you can do is use this technique, which I'm just calling quote unquote inspection, or sometimes I just say, we're just going to think about it. And this is, I know this why this is not students' favorite way, because you want to have a formula or something that's going to work every single time. But as you move higher up in math, there are some times when you just have to logically think through something and not rely on a technique. Okay, so how are we going to do that? If we're looking for the range, and we're going to assume that the range is between, two y values here, right? Like there's a smallest y and a largest y, that it's going to be written in interval notation. We want to think about then, what is the smallest output I could ever get out of this function? And the key thing to think about is these two terms here, no matter what you plug in for x, if you raise something to the fourth or you square something, even if I plug in a negative number, these two terms are going to come out to be positive, or the only number that would make it not positive is if you plugged in 0, right? You can't get anything smaller than 0 from these two terms because you're raising them to an even power. So if you were looking for the smallest output of this function, what number would you want to plug in to minimize these two terms? You would want to plug in 0, right? So I'm going to put note smallest output when x equals 0. And when x equals 0, what do you end up getting? You get the square root of 0 to the fourth plus 2 zeros squared, 2 times 0 squared plus 9, which gives you the square root of 9, which is just 3. So it stands to reason that the smallest thing you could ever get out of this function for y is 2, which is going to happen when x is 0. So the next thing we want to think about is, what is the largest output we could get out of this? So then you want to look at this and say, okay, now I'm looking for the biggest thing. And I have no restrictions on what I could plug in for x, right? So the largest output is going to happen when I let x be a really big positive number or even a really big negative number, because I'm going to square it. Happens when, I was going to put right, when y, how about I put is really big, really big. When I say really big, what do you think I mean? I mean when y approaches infinity. If you plugged in an infinitely large number, raised it to the fourth, that's going to give you an infinitely bigger number, infinity number. Add 2 times an infinitely large number, then this whole thing's going to be even bigger. Oh yeah, then go ahead and add 9 to that. That's not going to change it very much, right? So what it boils down to is, what is the square root of infinity, right? Because you could make this inside infinitely big. Well, square root, if you have an infinitely large number, the square root of infinity would equal infinity. So the largest output for this function will be infinity. And we didn't graph it. We didn't solve for x. We just considered the options, the smallest output and the largest output, and we were able to logically figure out that this is going to be the range. So if this was ever on a test or something, what work could you show? I would write these two down. I would write these two observations down. That way, if you get it wrong, at least your teacher knows what you were thinking, that you were trying to think about the smallest output and the largest output. Okay, let's try this for one more thing. Once again, we're going to assume that the range, there's a smallest y and a largest y. Okay, now for this type of function, this is a little different. I don't have a square root. Notice that the only thing that's ever going to change, if I started plugging in x values, the numerator is going to stay the same. That's always 10. So the only thing that can change is the denominator. And so what I would want to think about, if I was thinking about my smallest y value, think about this. Fractions are, I'm going to write it up here. Fractions, because this is a fraction, fractions are small, because that's what I'm looking for, when denominators when the denominator is what? What's the answer to that? A fraction gets small when the denominator is big, right? The denominator is big, this whole fraction is going to get small. So the question I'm going to ask myself then is, how big could this get? How big could this denominator get? How big? Well, hopefully you see that if I plug in a really, really big number, an infinitely large number, square it and add 5, the denominator could get infinitely big, right? So then the question is, what would happen to 10 over a really, really giant number, right? Because it's the denominator that I'm talking about, it's getting big. So 10 over a really, really big number, do you agree that that's going to get really, really small, right? It's going to be approximately 0. Think about it. If you had 10 divided by, a huge, huge number, and you punch that in a calculator, it's going to give you like 0.00000, right? Maybe and then 1 or something, but it's going to get really, really small as this denominator gets big. So we could argue then that our smallest y value is going to approach 0. If you have a fraction with a numerator of 10, it's never going to equal 0, right? This will never equal 0, but it'll get infinitely close the bigger that denominator is. Okay, so that was one. I'm not being very organized in how I'm doing this, but that's okay. So what's the opposite question? If I'm looking for the largest y value that I can get out of this function, I would ask the opposite question. Fractions are big, because I'm looking for the largest. Fractions are big when the denominator is small, right? When the denominator is small, fractions get big. For example, if you did 10 divided by 0.01, that's actually going to be 10 divided by 1/100. So you flip and multiply, that's actually going to be 1,000, right? So the smaller that denominator gets, the bigger the value of your fraction gets. So then I ask the opposite question. Maybe I should have, here, I know what I'll do. I'll do this in green. So then the question I ask is, how small can this denominator be? Well, similar to the previous one, x squared is always going to be positive or at the very least 0. So if I'm looking for how small that denominator could be, I would want to consider x being 0. And if x was 0, my denominator is going to be 5, right? How small can that denominator be? It could be 0, in which case I would get 10 over 0 squared plus 5 is going to give me 2. Now I know I said how small, and I'm arguing that 2 is the biggest, but what I meant by how small is how small can this denominator be, right? That's what I meant by how small. Because what that tells me is the biggest value for this fraction is going to happen when my denominator is as small as possible, which is going to be 5. So 2 is my biggest y value. And I can get it to equal to, right? If x is 0, 10 over 5 is exactly equal to 2. So this would have brackets on it. And I think this would be my range. I don't claim you can use this technique of inspection or thinking about it for any old problem. These problems were written specifically so that you could, because something is fixed, right? The numerator is 10. The only thing you have to think about is how big and how small the denominator could be, and that's not too hard to do. But if you gave me one of the other ones that we've done, I don't think, where I have my numerator and denominator are both changing, I don't think I could, by just inspection, figure out what the range is. Okay, so this wouldn't be an option to use on every single problem. But if graphing it doesn't seem to work because you don't know what the graph looks like, or solving for x seems to be impossible or very tough, this might be an option to consider.